Right, so in this lecture, we're going to look at shader coding. I think the first part of this we already have done before. So anyway, I'm going to go through that as well. We have done that last semester, I believe. But anyway, let's go ahead and start introduction to shaders. We already done one lab, I guess. But this is how you're going to code actually, so that's what we're going to do right now. So where is this data coming from? Well, if you're using 3D models, whatever you use to load into your graphic scene, uh, uh, those are the things you're going to pass to the shader code, and then you can alter your raw data into something different using shader code. So that is what the purpose of it. And we are actually the shader data is depending on vertices, colors, and the texture. The texture is not actually images itself. We consider texture as arrays in shader language, right? So any data sets with arrays, we call it texture, right? And lighting properties, of course, that is one thing that you can adjust using shader coding, and a little bit more things like shadows and things like that you can do, right? And how is it done? Well, basically the script that you are writing as shader code is running mainly in graphic card. So it is like graphic card programming, like GPU programming, right? That's also kind of a shader coding, right? So in this case, we're using the render time approach, which is whenever you're running a program, that is where it's going to execute everything on the shader. Okay, right, so let's move on. That is just a basic introduction for the shader, right? I think you have already seen this sample, the water movement thing. If you want, you can go to the lecture again and look at it. So I'm not going to pull it up right now. Program that can affect positions, of course, and also the colors of the pixels and things like that. So that's what we're going to use with it. And all right, so what are these things, what we are talking about here? Well, this is a light absorption. Well, that is like if you have if you want to make it little dim lights and things like that, you can take care of that using the light absorptions here. And the diffuse light, well, again, the lighting effects, right, depending on what kind of shadings you want with the light. So that's what it is. Texture mapping, this is actually the wrapping of textures, right? Well, there are two things that you can do here. One thing is obviously when we're talking about how you're going to wrap your texture, and are there any tessellation, which is a subdivision of polygons and mapping the right texture on it and things like that. Or if you want to take care of your texture separately and wrap it with a different pattern or things like that, you can do. Even you can change the image RGB values here, so you can do that using texture mapping. The reflection, obviously reflection is this. So if you have a light rays and it's reflect, and then whatever here you can see how it reflects on whatever the RGB color here, so you can see those. So that is reflection, and then also refraction, which is we already talked about this. If you see through water kind of thing, right? So if the light rays comes like this and it hits here and then refract, so whatever you're looking at from here is different, right? So only a little bit come to this direction, and the others is refract like that. Shadowing, of course, if you have a model like this, and then when the rays comes in hits, obviously you will see the shadow here, right? Okay, so those things we can handle there, right? And the surface displacement is mostly tessellation kind of things, right? Or you can apply the depth values and see how the displacement works and things like that. Especially MIP maps, not MIP maps. Remember we talk about things in the other 2D texture apps that want to see it like 3D, like a bump map kind of things. So you can do displacements on that when you're doing the bump mapping and things like that. Post-processing affects maybe the aliasing, right? And anti-aliasing techniques and things like that. Well, you can do that also using the shader code. So basically these are things that you do with that. Okay, right. So there are much more you can do. These are just a few of them that you can do, right? Here we're going to talk about what are the languages we're using for the shader coding, right? HLSL. This one is for DirectX only, so it is a DirectX. DirectX. That is what they're using for this one. So that means, yeah, if you're using OpenGL, well, this type is not compatible with this one. So if you're using HLSL, that is only for the DirectX. So if you're using a GLSL, on the hand, this will be compatible with this. So these two are two different approaches. If you're using DirectX, you cannot use GLSL anyway, right? Okay, so make sure you understand that. And then the CG is no longer there. CG is early the shader code, which is the alternative for NVIDIA graphic cards, because the NVIDIA came up with the programmable graphic cards. That means you can do a little bit more manipulation in the graphic side, I mean the GPU side. The other than the CPU can now program your GPU as well, right? So that's what this CUDA and CG was there for. So this one, this is, I don't think they support this anymore, but now you have cumulative unified device architecture, which is CUDA. This is only for NVIDIA cards, right? If you're using NVIDIA card, you can use this programming language to program that. Well, so that means, is that all? I mean, you can use the GPU programming using this library, which is called OpenCL, which is other than NVIDIA, if it is a Radeon or Intel, if it is a compatibility, if there's a compatibility for the programmable level in Intel graphic cards, you can use this OpenCL. So that is another option that you can do. So all these are shader coding programs. There were a few more out there, but I don't know what they're based on. So these are very basic fundamental programming languages for the shader coding. Okay, right. And then compile to assembly means, well, whenever you do this, whatever you written is a script that you're writing, and that script or the language that you had to compile, of course, and you having an assembly code after you compile. So that means assembly is nothing but taking care of the registers and say move from one register to the other, if you want to handle everything in a register level. So that's what the assembly take care of, right? So then so that is one thing you have to keep in mind. This is not like anything else that you have done, like Java. You don't have a compiler like the compiler in C++. Compile it and give you executable file, and the Java is a little bit different from that. uh, and so these are behaving separately, but assembly is the main, the core on graphics shader programming. So you have to convert it to assembly code and plug it to your main program when on the runtime. So that's what it does. Okay, so right, so when you compile this, usually it's compiled on a GPU side, so that's what it is. Compilers are on the GPU, obviously. And why? Well, if you're using something like NVIDIA, right, um, GPU has to handle all the code that's related to this, right? So this is the GPU part. So that means the compiler has to do something with the GPU architecture, right? So that's why the compiler is running on shaders, GPUs. Okay, right. And then yeah, when does the compiler take into action? Well, it comes in runtime. Okay, so whenever you write a program in your, what is the part that you're running on a CPU, and you embed all these shader code in there, right? And then this is vertex shader, fragment shader, whatever you want to call it separately. So whatever you have here as a shader script, you can have many multiple shader coding if you want. Whatever you do there, only time when you execute this program, right? When you execute this program, it will go and grab this script, and then you compile it, and then you link it, right? Compile and link will take care here, right? And then it will be a one program. So that is the process. So you will have these separately when you're writing, right? Okay, so then the so whatever you do, when it's done on running time, means you don't have uh, when you're typing anything on your IDE, which is your developer interface, uh, it doesn't give you any errors, right? So only error time that you get errors is when you print the log of the compile logs of these two, uh, or when you're running it, you can figure out there are some logic errors if it is, right? That's the only time you figure out if there's any errors, right? Okay, these days most of the IDE is coming up with auto correct or auto check. That won't be there, so it is very low level coding. It's not that efficient yet, but I have seen some websites which is handling this very well, especially with the WebGL. When it comes to the surface, there are so many ways that you can write this code, right? Okay, so all right, so here we just talking about the same thing that we did before. What is HLSLEs? It's just a C-like coding, and then also this one. Why is it not compatible even with C-like? Well, here we have GL underscore. As in this code we have GL underscore as a key identification of the keywords. Here you don't, if you put this one, doesn't make any sense on this one, so that is why it's not compatible. So this one says GL means whatever is related to OpenGL, we're using a GL underscore here, right? Okay, so so that's why it is not compatible. These two are not compatible. Well, this is outdated. I would not talk about that much, and I think this one is gone too. So those are very old languages. So these days you have CUDA instead of this, and OpenCL, right? So why I put renderman's the Pixar's renderman, because this is very old and the pioneer of this. So these are the people who actually introduced shaders. I wouldn't say only people, but they were in the top long ago. But well, nowadays it's changed, right? So okay, so what are the shader codes we are interested in? What are the shader types out there? So that is what we're gonna look next. The types of shader, right? So there are two types mainly we are looking at. Okay, one is called vertex shader, right, and the other is fragment shader, or I call it pixel shader. So in vertex shader we using always be using x, y, z values, right? So this is positions actually. These are position handling, and this one is color handling, RGBs, right? So those are the main two, vertex shader and the pixel shader. In the pipeline, first you handle vertex shaders, right, and then later you handle fragment shaders, right? Okay, make sure you understand that and remember that. So these two are handling in a different places in your pipeline. Okay, right, vertex shader and then the fragment shader, right? And this is something that you can use with the modern OpenGL geometry shaders. Mostly if you can do cloning. So if you pass one object, you can make more, right? Or you can do the subdivision, right, and things like that. So that is a geometry shader. I think it's related to I think a compute shader, or this one, or the both were related to tessellation as well. The tessellation is fixing your let's say if you have a terrain, right, like this. So you have terrain and you subdivide this one to move further, or the LOD is coming into play. What is LOD? Level of details. So if it is come closer, you may be subdivide this better, but in the far away it is not, right? So anyway, if you do something like that, so subdivision or something like that, what happen is let's say I have, this is my object in the far distance, so it is very flat and you have a texture on it, right? So on this texture you need only worry about texture code here, texture code here, and texture code here, and then you can bind the image into this. But if you do when you come closer, right, let's say I want to generate some terrain on it, so like a little bumpy looking like this, right? So in that case what you had to do is you had to subdivide this, right? You had to subdivide this. So when you subdivide this, well, I still have my texture code mapped into only this, right? So what about my bumps, right? Now I have a different look that I want to emphasize there, but my textures are not right, right? It's not tiling right, it's not right. So in that case I can make this texture code much more precise and make it plug into this with a bumpy look and all that. So that is what the tessellation process actually. So it will, when you get come closer and closer, if you want to make it more looking detailed structure instead of just a plain structure with the image, you can reverse, you can make it more efficient. So that is a tessellation process. So personally I never use this on compute shaders, but the geometry shader has to do some role on the tessellation as well. I think mostly compute shader is for that. Well, I'll leave you to figure it out. You can read a little bit more further and see whether the compute shaders are for what are the things that they're going to use for. Okay, right. So then let me talk about these things a little bit more. The vertex shader and the picture shader. So those are things we are focused on mostly in this class, right? Okay, so let me see what are those are, and let's move on a little further. Right, so uh, here we have the vertex shader is for control transformation, right? So this is what the rotations, scaling, uh, so you name anything like dealing with x, y, and z, right? So that is what they are using for. But what about light operations? What does that mean? Well, the lighting is, you would say it is RGB values. Is that all for the lighting? That's the only question that I have to ask here, right? So basically, if you're using a surface, right, in order to get the light, right, and then a reflection, of course, right, and if you're looking at from here, right, so that is where you decide what color the RGB value is supposed to be there, right? Okay, so that means the color value. So in this case, what angle do you consider this to reflect? So that is where the normals comes into play, right? So normals are, if you take one triangle, if you get two vectors on this and you calculate the cross product, you can get the normal of it, right? So that is what this normal vector is. So then you can decide this theta angle, when it hits here it will reflect on the equal the angles here. So in that case you can decide how much illumination I should give here, right? So in order to do this, you have to calculate the normal. Normal is nothing but xyz value, right? So in that case, we have some part of the lighting operations has to do with vertex shader. So that's why it comes into play, right? So that is what lighting operations means. And yeah, the pixel shader is only for RGB values, okay? RGB values, and ultimately decide the final pixel colors before rasterization. So what is rasterization? Well, if you have a 3D model, right, and this is your 3D model, and I've just rotated in some angle and zoom it, or whatever I do those operations here in the vertex shader, and then what you do is you have to map this to your 2D screen, because you're looking at in a 2D screen, right? This is your computer and it has only 2D screen here. So that means you have to always convert this 3Ds to 2D. So in order to do that, we're using something process called rasterization. So that's what this rasterization comes in. So this one, the color decision on this will be just before that. So if you remember the pipeline, the rasterization and fragment is get closer each other. So that's the reason, right? So this is why I said vertex shader is the first one to execute, and then you follow the fragment, right? So those are the sequence. Well, I have some samples of this. I think we have seen that before, so I will skip this. If you want to really go and look at it, you can go to the lecture notes and look at these things. So the ocean demo and then these things, those are from the websites out there, right? So you can look at how these shaders as examples on this, right? So I will move on from here to the next slide, which we're going to talk about the attributes, right? How are you going to pass data and what are the types? So that's what I'm talking about here. There are four ways the shaders can receive data from the CPU to GPU. I mean, the CPU, they're receiving data from CPU, right? One way is buffers, of course. So we have used so many ways buffers in our we learning of buffers these days, right? So the VBO is one way of sending data, right? VBOs. And the other is uniforms, texture, and varying. We will look at these things in the next slide. but attributes and VBO, the buffers are nothing but uh, the examples I can give you is VBO, VOAs, that is a vertex array objects, right? This is a vertex buffer objects, and pixel buffer objects, right? PBO, and there's another one, FBO, which is a frame buffer object, right? Frame buffer object. So those are the buffers that you can use. There are more buffers. We will do one lecture on those stencil buffers and all that. After we cover the shaders, I will move into buffers a little bit more. Okay. Right. So these are the things that you can use here to pass the data, right? So you can use any of those things. Okay. So what are the uniforms? What are the textures? What are the wearing? Why we're using that? So that's the next question we have. So yeah, let's look at that. Right, so here we're talking about uniforms. So uniforms are like, for example, when you're writing your script. So this is where your vertex shader comes into play and the fragment shader comes into play. So let's say you have vertex shader here, right? And then this is your fragment or the color, right? The pixel shader, whatever you call it, right? So usually these are scripts, so this has a main function in there, right? And then this one has a main function in there, right? So those are separate programs actually. And then you will have some functions if you want, F1, whatever you do, you call it here. And this one also has some functions, right? So whatever you do here as a global, you call it uniform, right? So that's what uniforms comes into play. You can write and define your variables there. It will be global to this, but it is not global to this, right? So these are two different programs. Okay, so these are belongs to this guy, has nothing to do with these ones, right? So whatever the global using uniforms is belongs to this program. If you're using uniform here, it is belongs to this. So that is the global variables that you define in any of the shaders, right? And then the textures. Textures are not images itself. Those are actually arrays of data. Okay, so here you can pass the image as an array of data. Right, so that's what this is talking about here, image data, right? But image data is always a texture, and textures are, you can say, vertex data as well as all the things that you do in your model loading. When you do the 3D model, you can pass it as a texture, right? So that is what the textures are for. So you can have a large scale of data transferring. So when you're looking at texture here, it is not the image that like you're using in any other term that you're using for images. Okay, so here texture means data array, right? Keep that in mind, especially in CUDA. We talk about this a lot, but each time it is not going to be texture or an image. In that case, texture is not an image, right? But it's a set of data. You can pass image data as well. Okay, right. So then okay, so whatever you do here, as I said before, you have to have normals and all that calculations in order to decide what is the RGB value in there, right? So that means from here to here there has to be a connection, right? I had to pass some data or the positions XYZs to this guy to decide what are the colors I want to use. Okay, so in that case, especially we're using this variable, which is a wearing, right? And if you type a wearing float A or whatever, you can pass some data from this guy to this guy, right? So that is how you exchange data, right? So can you do vice versa? Well, if you know the architecture and the pipeline, this guy, which is a vertex shader, is executed before the fragment part. So in that case, this is highly unlikely you can take the same variable backward, right? Because this one is executing first. So I would say the varying is for passing the variables from the vertex shader to the fragment shader. Okay, so that is what we doing this using these things. Right, so those are the storage qualifiers. So what you're using in shader program, and you can use these to pass handle data. Right, so then you know how to handle the data. Now we have to look for what are the data types that we're going to use. Right, okay, so these are the data types. So yeah, so position, you can be XYZ, right? XYZ. So it can be float, it can be many other things, right? Yeah, double, float, whatever it is. And then normals also, nothing but float. So where are these coming from? Well, if you take a 3D model like a wavefront loader that we written, right? So you have V's, right? Yeah, we have V's, and then we have VTs, which is nothing but the vertex texture, right? And then we have VNs, which is the normals, right? Okay, and then we have colors, if you want to color C or VC, whatever, right? It depends. And then also we have what? We have faces, right? Okay, so well, these are the types on the 3D model actually, right? So well, the normal, this part right here is XYZ. This position and this position right here, we can consider this one as object position and this one as actual V's that we're talking about here, right? So it can be either one like that. And then color is RGB, of course, right? And this one also X and Y, which is a vertex texture, right? So everything, most of it is XYZ. So that means it's related to what? These things are related mostly into vertex shader, right? It doesn't mean that I'm not using anything on the pixel or the fragment shader which is related to this. Of course, I using a varying, and then I can pass the data into that, right? But mainly the data types we're handling is in the vertex shader, right? Okay, so that is what these types. There are more types that we're going to look at. So the next slide is about more types that we're going to look at. Okay, right, so this part actually I did not cover the last semester, so these are new things that we're going to talk about here. Okay, right, so this is about non-vector types. So what are the non-vector types means? Well, remember this name. If I ask you on the exam what is non-vector types, you should know that, right? So the Boolean is one, which is talking about true and false, just like C, right? And then the other one is integers, signed integers. So what is signed integers? What is the difference between a signed and unsigned, right? So well, if you get the register, you get two registers like this. Sign means the one bit is allocated for to indicate whether is it negative value or the positive value. So in that case, you will have only 31 bits to store the value, right? So the maximum value is 2 to the power 31. In this case, you don't have the sign, right? It's unsigned. So that means I have length of 32 for the value. So that means I have 2 to the power 32 representation of this. So whenever you're using unsigned integer, the advantage is, yes, I have all the whole length of this to represent numbers, but here it will be limited, so this is the problem, right? Okay, and the floating point numbers, how do you represent floating point numbers? Well, let's say I want to represent something floating point, so I can have something like this, right? And usually you put the point here. So this number is 2000 in that case, right? So what this means is actually you don't need the 0 here. 0.2 multiplied by 10 to the power 3, right? So this part right here, you represent, first you represent the plus or minus, and then you represent the number, and then you represent what is the power right here, right? So this is the number you do, this is the value you do. Okay, so then it's plus or minus, and this is 32-bit for the single precision. If it is double precision, you will have longer, right? So then plus or minus, and then you will have longer representation of this. Okay, so that is how you represent each value. This is double floating point, this is single floating point. So I'll have a little bit longer and a bigger register for the double, right? So those are the differences, right? But anyway, these are common things for CC++ as well, right? So it is the same for the shader coding, right? So let's move on, and then we'll look into matrices and vectors and what are those are. So here you can see when I'm talking about the vectors, I have B vector, B2 vector, and B3 vector, and then a B4 vector. So okay, so the Boolean values are the B, but what does it mean by vector 2 for the Boolean? What does that mean? Well, usually vector 2 is x and y, right? So we know that already. But here it says, okay, the true or false value will store in this position, and true or false value will store in this position. So that is what B vector 2 means, right? So on, if it is 3, it's 3, like that, right? And here also the integer portion of the values will be stored here, right? And this is the floating point. Well, usually you know this is vector 2, and this is vector 3, which is x, y, z, and this is vector 4, which is x, y, z, and a w, I'm sorry, right? So this is w right here, right? What is w? Well, if you're talking about the homogeneous coordinate system, right, the thing is you have to have 4 by 4 vector. So the last row right here is 0, 0, 0, 1. So this is where this w represents, right? Okay, so that is where the 4 comes into play. And the matrices, of course, you can have 2 by 2, right, and 3 by 3, and the 4 by 4. Those are the matrices representing there. Well, 1 by 1 doesn't mean anything, right? So 2 by 2 is like this, right? 2 by 2, right? And then 3 by 3, you have 3 rows like that. This is 3 by 3, and 4 by 4, you have 4 values like that. And then of course you can have, so this is x, y, z, and w kind of thing, but you will have matrix here like that, right? So this is 4 by 4, right? So so these are the ways that you can represent vectors, and these are inbuilt in the shader code. So in that case, you don't have to worry about it defining anything, right? So you can use that straight. Okay, so then sample 2D. Well, sample 2D is usually taking texture values, right? Yeah, usually textures are always x and y, right? If you're talking about texture code, x and y, and so the coordinates only represent 2 values, right? So that's why it is texture 2D is here, right? Right. So that is why you say, well, let me go back. All right. So that's the reason you will talk about this as a 2D right here, right? So this is 2D. And the sampler cube represents a sampler cube or the texture 3D. What does this means? Well, I will have x, y, and z coordinates. For example, these are new things actually. If you're using a skybox here, the skybox has 6 sides, and then all has so values, the texture that you wrap in. So instead of using only 2D, I can set up the 3D texture and set these XYZ values properly, so you can have the cube sampler. So that is where, when you're creating a DOM or something like that, you can use this the cubic texture coordinates. So that is fairly new. It was not there long ago. So you can use that directly to make this the DOM or the skybox and things like that, of course. And this is nothing but the void part, which is nothing but you don't return anything. So you can write functions with that, just like C. Right? So those are things, the specialized data types that you can talk about here, right? So I think it is clear enough, right? Okay, so after that we move into constant values or literals in shader coding. Well, there are a few more here that I had to introduce. There are 3 base structures, right? One is a Boolean constant, either true or false. Of course, we know that already, right? And then the integer can be specified by decimal, octal, or a hexadecimal. So this is one part that is very important for you to keep in mind. So if you're using values like base 10, right, obviously just write it like this. But if you're using octal values, so that means the base 8, right? Yeah. So in that case, usually you put a 0 at the beginning, right? So if you have the number representation in a base 8, what you do is you put a 0 in the front. Okay, so that is that. And if you're using the hex code, right, especially where the hex code comes in, well, the RGB values sometimes using a hex code, you know that, for the colors, right? Right, hexadecimals you call it, right? So in that case, you put O and X in the front. So if you see something on the shader code with the O and X, that means they're using the 16 base 16, the color code, right? So, or anything else. So that is gamma corrections and all that. Yeah, of course they're using that. It doesn't mean that this gamma is that, but yeah, that is lighting and RGB values. So you can use 16 base. Okay, right. So that is this is one thing that you have to keep in mind, depending on the base. So I would recommend to remember this slide for your exams as well. So I like to point out that. So keep in mind this one right here. Right. Okay, so let's move on to talking about more variables, right? And the floats, right? So there are a few ways that you can represent floats in shader, right? So these are the ways. So you can use one point like this, right? So this will consider as a float, right? It won't throw errors if you do that. Or you can just the regular values that you do, right? Anything like that. This is also wood, this is wood, and also it will give you the mantissa and the radix and the exponent. So this is what means. So if I say 2 to the power, right, something multiply by 10 to the power 4, right? Right, so this is the mantissa part, and this is 10 to the base part, and this is 4, which is the exponent. So this is the order of it, right? In this case it is if you write 2.4 multiplied by 10 to the power minus 2, that's why it shows here, right? So the whenever you want to represent it in the E base, just like your calculator, you can represent that in shader coding as well. Okay, Right, and the constants, yeah, the pi, it is not inbuilt, so you may have to define it. The constant numbers, you can use the word constant just like C. You can do that. Okay. Right. So let's look at how you define the variables, and whenever you want to do that, how do you define variables, right? So here it is. When you naming the variables, what you do, right? And so let's talk about that. Okay, so how we going to name variables, right? So the variable names must be start with a letter, right? That is the first thing you should know. You can use any letter you want. Like for example, I can use A to Z simple or A to Z capital, right? And yes, you can start with underscore, right? Right, that is also possible. So I can define something like underscore uh, model or something like that. Yes, I can do that, right? And yes, I can have the values from 0 to 9 obviously, uh, but yeah, only values it's not possible. I think you have to have some letter contains. Okay, and the user variable names are not allowed to have gl underscore, right? This is only for glsl, right? If you're using HLSL, yeah, you can, right? Not for this guy. Okay, so why? Well, this is these how the keywords are defined in GLSL. So in that case, you cannot have that, right? And all the variables must declare before they can be used. Yes, not like Java or anything, JavaScripts or anything. In this case, you have to define it at the beginning or the prior to use it, right? Right, variables can declare with or without initialization obviously, but you should have some values. So here it is example of this. I can define alpha without this, or I can initialize something. Okay, and the good thing is the struct types are possible in our little shader code, and that is also a good thing, which is we can use uh, the structure types. Okay, so let's talk about that. So here I have, instead of the variable that we're going to use in any other the forms, which is a float or anything like this, in this case I have one structure called my light. So it has the intensity, position, and the color. So all that, so the position here is x, y, and z, so that's why I have vector 3, and the color I have R, G, B, okay, red, green, blue, and what is this fourth one right here is alpha, right? So this alpha value take part of a lot of things, especially when it comes to PNG values. If you want to have the transparent, you already know that, right? So this RGB value here, and this one is just a float value, right? Okay, so how are we going to use this? What are the ways that we're going to define variables? Well, we can look at this example right here. Yeah, so so these are the ways of arrays are defined here. So you can see the frequencies of 3 means, yeah, you have 3 float numbers. This is how the 3 float numbers is laid out, just like C, right? And this is just a one number, has nothing to do it, right? So but it's a constant value because I'm applying it here. So this means this guy is only what, 2, right? So these are 2 structures, so that means the previous slide that we saw the structure, so 2 of them right here, right? So it is the array of structure, so that's why my light is the type. Okay, so those are just like C, so I don't have to spend a lot of time explaining this. This is the same thing that you No, CC++, you do coding with it. So these are just like that. Okay, so these are the things that you never seen before, I guess. If you have seen this, that sounds good. This slide and the rest of it beyond this level we had to talk about. Right, so the individual elements of a vector can be represented using the array notations. So that is the one way of a vector that you can define, or you can have a dotted notation. What is this? What does this means, right? Well, if I have a vector, how do I define a vector? Vector 2v, let's say like this, right? So this means what? I have x and I have y, right? Yeah. So either I can say v dot x, v dot y, or I can say v 0, v 1. So that is the representation on this. Okay, so that's what it says there. So you can have both ways, right? And also the name of the vector components also depending on these things, like for example xyz is the example I just showed you, or you can have, of course, this also possible, right? This also possible, b or v 0, v1, v2, and so on. So you can define like that, or using these things as well, right? So these are different ways, different times that you're using these colors or the positions or the texture code. These are for the texture code if you've never seen this before, right? So that's what they're using it for. Depending on your usage, it will fall into any of these. So it will automatically get those generic data. So these are generic data. When you're accessing, you can access either way of these 4 types. Okay, right? So it is always access single component, right? So anyway, so this is how it's structured, right? So let's look at something else which is also interests me a lot when you're doing the shader coding program. So this is alpha initialization of vector 3. So this is how you do. You call the encapsulation or you have to say what type it is. So vector 3, and then this will be x, this will be y, this will be z, right? So that's how it's decide which one it is, right? If you define a vector 4 like this, either it can be x, right, y and z and w, or it can be r, g, b and a, or it can be s, t, I think pq, yeah, so that's what's 4. So you can have any of those, right? So then let's say I have alpha xyz is equal b in this case. So this b guy right here will become what? Will become nothing but this value, right? And then I can say alpha 2 is 0, 1, 2. This is the third one, right? Third value giving to the d here. So the d is a float. Take the third value, which is this. Or I can say a, which is a vector 4, is equal alpha xxx. So the x value of alpha is nothing but 1. So in that case, the whole thing in my a will be ones, right? And then also if you say the vector 2, right, z and y, so it will be z is 3 and the y, I mean the x is, I'm sorry, this is x is 1 right here. So that is that. And then now gb values, if you have alpha dot rgb, right, so the b is now nothing but 1, 2, 3. So you can see here, either I use this form, either I use this form or this form. So whatever you use here for the alpha, it will take care of this in order like that. Okay, so that is one thing very interesting. and if I use y is my 2 here, right? But the problem here is a is vector 4 right there, right? So the vector 4, if you set up only two values, that won't work. In that case you have to have either xx or something like that, then it will work. Otherwise it is a compile error. So this is what it is. Okay, so that's, you have to match, you have to always match the size. Okay, so that is important, the factor here, right? So the sizzling notation is another interesting one. So let's look at that. What is sizzling notation is, right? So this is what sizzling means, right? So that is nothing but, yeah, these values right here that so if you have alpha as so let's talk about this. They're using multiple properties of name to create a new vector called sizzling, right? So you have multiple properties, property names to create a new vector. So that's what it is. Sizzle notation can be used. Sizzle notation can be used to the left hand side of an assignment. Of course, that means so the left hand is this side right here, right? And then we actually using this a lot in our program. Okay, so make sure you understand this one very well. Only problem here in the first one is this one right here, right? So alpha usually have x, y, z. So in that case I can use x and y, but I cannot have xx. Only xx part is coming to your right hand side, so the assignment. So in this case it will give you error for sure, right? But here I have all three component addressed with a vector 3 value, so it will be fine. So there's no problem in that. But here also I have the two values there, and then I'm assigning, so it is not a duplicate value, so in that case it's good, right? For the last one right here is I have three values in this side, right? X, y, and z, but I have two only here, so that is a compile error. Most common compile error is this one, right? Make sure the sizes matches in the both sides. Okay, so that is also important. So, and then keep in mind this one. So I like you to keep these things in your mind for the exam as well. So I would test you on this sizzling notations. Okay, so keep in mind the ones I put asterisks. So those are things that would come to your exam. Right, okay. Right, so let's move on some examples, more examples on shader coding, right? So this is another one, the conversions, right? You can convert data type one for the other, and of course the casting is available for you. So this is just a value assignment, and I can say the float version of this. So this is a float version of that. Multiply by 2.3 will give you the b value, right? So this is casting actually, right? So the casting is actually when you do the vector 3 vector 2, this is also casting. You have seen this one right here, this one's also casting, right? And yeah, this is just assigning values here. This is the important one. So I have only two components here, but I'm passing three values, right? X and y and w. So you can define it like this as well. So this is possible to do, right? And then also either you can have, this is only one value, which is because it's only one value from alpha and three values from beta will be the gamma, which is gamma is 4, right? So that's also a cool way of doing things, conversions. Okay, so those are things that you can do, right? So let's look at built-in functions, which is we are oftenly use or mainly use in shader coding, right? So these are the things that we using for the trigonometry. Radians, so there are degrees, right? And then the sine, cosine, tan, and then the inverse of that. So this is the inverse of sine, inverse of cosine, inverse of tan, right? So these three right here. So you call it arctan, arc, cosine, and sine. You would call it like that. The exponential powers, yes, x to the power. So the exponent values, right? And then the logarithm, right? Square roots and inverse square root. So all that is there. So yes, you can use any of those things. And absolute values, right? Sine, flow values, ceiling, right? What does that mean? So if I have 3.4, flow value is 3, right? Yeah, usually everything like that. 3.6, the ceiling value on this is 4, something like that. So it is ceiling or flow. And factorials, mod, min, max. Clamping means it seems like something similar to this. And then the mix values means you just get two values and just get the average of that. And the steps and the smooth steps means if you give two values, right, it will break it into smoother values. So that's called steps, right? And make it happen between these values. So it is pretty interesting one, which is a smooth and the step. I think I'm talking about that. If it is not, you can look at it on any tutorial. I thought I have some examples of this. I'm not sure, right? But anyway, yeah. So the geometric and the matrices, we have a length, distance, dot, cross. So those are cross products, dot product, cross product. Normalizing things means if you calculate the normal, you divide by the whole length of it, right? So you can do the normalize, right? And then the float transform and the face forward. I never use this one. So this is like a cull facing kind of thing, so you get rid of the back side of it. And the reflection value means if you have 2 2 3 3, obviously reflection is, if you're using x reflection, you will get something like that, right? So it is just a reflection. And matrix computational multiplication. So this is a multiplication of matrices. You can do that. So there are more kind of things that we do, the vector relations, texture lookup. So let's look at those things a little. So I'm not covering the whole the shader programming. These are very important ones that I'm just pointing out here. There are more. You can go and if you're really interested into depth, you can go and look at the others. So the less than or equal, greater than. So these things obviously you can let me go there, one more back. Yeah, so these are some functions that you can do. You can use the keywords, or you can use actual these things as well, right? So there are two more union keywords as well that you can use, right? Texture lookup, you can do 1D, 2D, or 3D, right? XYZ in here. And the projection, 3D projection, is actually for I never used that before, but it is for the perspective projection, I believe. So that's what they're using that. And the texture cube is for the skybox kind of things, mapping, right? So you can use that. Shadow mapping, of course, using this. We did not cover that. I'm planning to cover that if we have. Yeah, I think I have enough days to cover these two. So we'll look at those as well, how you do the shadow mapping and things, right? So we'll looking forward to cover that one in one lecture, hopefully. Right, and then the fragment shaders, df dx, df dy, and these things are actually uh, uh, talking about the effects of lighting effects and things like that, you know, the explosion and all that, using some FX libraries. So these are some of these are useful in that case, especially when you're using a FX, it's called FX library, right? You can design something and then directly call here. Uh, that you can use a designer package, like for example the software, to have some effects on it, and then you export it and then use it, right? So the shaders only. So the fragment shaders, actually this is talking about the lighting of an object. And noise, well, I did not use any of these, the noise factor, so I cannot say much on it. This is also about how you're going to handle the images. Probably, I'm not sure. I'm going to pass this these two here and here. Don't have much experience on it, right? But you can always look at if you want. I'll just put it out there because those exist. So keep aware of those things as well. Okay, all right. Okay, so let me look at more vertex shader built-ins and the things that useful for us to work on. This is what vertex shader actually returns. What is it returns? Always the position x, y, z, maybe w. Right, so it is a vector 4 is always this, and the point size sometimes, right? And then clip vertexes. The clip vertex is something that obviously the clipping of objects in the screen. If you don't want to talk about this, you can get rid of it like that. So you can clip anything you want, right? Especially in the depth buffers handling these clipping things, right? So what does that means? Well, if I have one object in the front and if I have another object in the back, right, there's a part which is I have to clip off. I don't have to do anything with this part which is covering by the front object, right? So that is kind of a clipping techniques that you can use, right? So that is something that handling in here, that's what they're saying. But this is the one which is mainly returning in the vertex shader, right? Every executor vertex shader has to have this one. That is the end. This is the last part that you do in the vertex shader, right? And well, yeah, it's may, so you can notice here these are may, but this is must, right? So you have to have that. So yeah, so this is a conjunction of the clipping planes that we are talking about, these things right here, right? So yes, and then at last let's talk about the attributes, built-in attributes. So these are the built-in attributes, especially for the multi-texture coordinates. So GL color is one which is actually talking about the fragment shaders using this, but you can have access to this in your vertex shader, right? And then secondary color, well, I never use this. This is also the color maps that you're going to use, so you can have the secondary, and the GL normal, obviously, that is taking care of the XYZ normal of a triangle or the polygon, and the GL vertex give you XYZ values of this, right? So that's that. And then the multiple coordinates of these are nothing but the images that you're going to load into one. So if you have anything that loading images into your the model map or the cards that you're going to use with the pictures in it, right? You can assign up to 6 or 7 multiple textures and then handle those, or data structures, whatever you want to do here. Multi-texture coordinate system, so that's what it is, that you can use RGBA values of this image. And the fog coordinates is a new one, which is I mean, it was fairly new, it's not really new. This is a fog. If you want to apply fog into your system, you can directly use this just give you a little bit the whitish smoky looking pictures when you're using that, right? Okay, so this is not the complete shader coding structure. You can carry on studying this if you really want to become a shared expert on coding. I give you just a brief touch up, how are you going to use, what are the things that you have to keep in mind when you're using a shader code. Okay, so the next lecture, yeah, we already covered that as well, I think, even when I'm teaching you the lab. But anyway, I will post a lecture on that as well, on the shader. So once we finish the shader, let me shift to buffers a little bit, talking about, but only thing, those are actually the language related, so that's why I'm not going to push it that much. When you're learning computer graphics, you should learn graphics, not about a specific language, right? So these are also specific language. So this is a GLSL language. This is totally different from what is HLSL, right? So that is two different structures. So this one is I didn't even touch. So that's why it's just a language specified. So again, when you're talking about buffers more, that is also language specified, which is OpenGL only. So that's why I'm not pushing that much for those kind of lectures. I like to introduce you much more important ones, like animations and stuff like that. So we're looking to look forward to cover a little bit interesting ones. But WebGL is one more interesting one, mostly people using these days. So I will cover that at the end of the semester. Right, so I will see you in another lecture. Right, so this is all for this one.